don't even know when water is going through here. Orbital line or
I'm not sure if you guys have checked the Canvas page. I uploaded the model answer for homework 1, 2, and 3. I believe homework 1 and 2 is graded. Quiz 1 is graded. I'm not sure about quiz 2 and homework 3, but it will be graded soon. If you have any question about homeworks, about quizzes, you can stop by during the office hours. If the office hours doesn't work for you, send me an email. We can set up a Zoom meeting, because I know many people have questions about the quizzes and how they are losing grades. But wait until the quiz is graded, and then you have problems, you come to me, and then we will solve the problem, okay? And wait until I upload the model answer for the quiz, so that you can see what did you do. I have an announcement for the quizzes. The quizzes contribution, do you guys know what we agreed on? 25%, right? This is gonna be changed. This is gonna be 15% after some circumstances. So quizzes are gonna be 15%, and we are gonna have about from 7 to 8 quizzes. So each quiz is gonna have 2 points, okay? So if you got 0 in a quiz, that means that you lost 2 points from the 100 point for the class. Okay, so this one thing. But the good thing is, let's say that we are gonna have 8 quizzes. I'm gonna take out the worst quiz. So I'm gonna only grade 7. If it's 7, I'm gonna take the worst quiz and I'm gonna grade 6. Okay? Is that fair enough? Okay.
So if the quizzes are from 25% to 15, that 10%, where does it get distributed?
5% to the first midterm and 5% to the other midterm. So our exams are working on. Yeah. All right. So last time. Oh, okay. Oh my God. All right. Go ahead.
Homework. We didn't put any percent on the syllabus.
It's 5%.
5. Okay.
Yeah. And actually, not all the homeworks have the same grade. Some homeworks are 20 points, some homeworks are 40 points. So keep attention to the number of points per homework. Yeah. Yeah, our midterm exam is on Wednesday next week. So
Wednesday?
sorry, Thursday. Yeah, I'm sorry.
And we're taking like
During the class, I'm just gonna confirm with the department if I can get extra time either before or after. So, do you guys have classes 30 minutes before the class?
Yes.
Yes. 15 minutes before the class? 15 minutes after the class?
Yes.
Okay, so the exam is gonna be the time of the lecture, okay? Alright, so we are gonna have, alright.
COP we arrived like a little bit late.
What was that?
COP we arrived like a little bit late.
Who arrives a little bit?
To the exam?
Oh, okay.
Because
Well,
I have class like on the other campus.
okay, so alright, we can have like, if somebody arrived late because of like emergency thing, I can take him back to my office and we can continue the exam, but it should be emergency.
Obviously, the video's kind of crooked.
What was that?
The video's kind of crooked.
Video,
I got it.
okay, let me fix it. You guys watch these videos, is it helpful at all?
Yeah, that's something.
That's good.
Is it working? Yeah, I think it gets everything. Yeah, okay. Alright, so last time we started the Newtonian kinetics and we said it's only one equation. The sum of the forces equal the mass multiplied by the acceleration. That's the only equation in this chapter. It can have different formation, like if we are dealing with xy coordinate system, so this equation is going to be divided into 2 parts. Sum of fx equal the mass multiplied by the acceleration in the x direction. Sum of fy equal the mass multiplied by the acceleration in y direction. We're going to do the same thing with the tangent normal and the polar coordinate system. And that's what we are going to do today, is that we see how we are going to manipulate the Newton's second law to fit for the curvilinear Newtonian kinetics. So let's start here. Right now, chapter 13.5, curvilinear Newtonian curvilinear, that means that we are gonna have tangent and normal. And the way, do you guys remember why we use different coordinate systems? Why sometimes we see, we use Cartesian, sometimes we use tangential? Because of? Depends on the motion, right? So if you have a motion is in a linear path, so it's convenient to use XY coordinate system. But if it's a curved path, it's gonna be very, very hard to use XY coordinate system. That's why we manipulate the coordinate system so that it can make our problem solving process much easier, okay? All right, so let's see how the curvilinear motion look like, and actually there is a really good application that shows the curvilinear motion, and actually that helps me in my undergrad when I was studying transportation, when we designed the curves, the geometric design of a road network. Like if you have a road, if the road is linear, there's nothing to do with curvilinear motion. But once you want to exit the road and want to move on a ramp, like the road is something like this, and somehow there's an exit, and the exit is something like this, right? This exit, once you are moving on the road is like, doesn't have any slopes. The only slopes that has is the rainfall slopes, like so that the rain can discharge it to the manholes on the side of the road, and that's normal. But once you get to the curve, the road will have a super elevation. And actually this super elevation is designed so that the car doesn't leave the curve. So, because once you get into the curve, so that the car can maintain being on the curve, it needs to develop a normal acceleration. This way, why? Because the car is tending to like be thrown out of the curve. That's why the curves of the road has a super elevation, like something like this, so that you can create a component from the weight of the car that goes this way to balance the normal acceleration, okay? So let's assume, yeah.
I just have a question. Have like with these curves, if it's too much, doesn't it get dangerous for like the car to like lose traction?
That's why when we design the curve, it depends on the speed that you want on the curve. Because if you guys remember, do you guys remember what is the normal acceleration equal to?
Velocity square.
The velocity square over the radius, right? So when you get into an exit for a road, it says that the maximum speed is 45 miles per hour. So if the speed got bigger, so that means that you need the slope to be much bigger. And that's what happens when you have like, you know, the Formula One, they have a lot of curve. You will find that the slope is very high because the speed is very high. So that's why you need more slope, because once you increase your speed, like let's say that you having a curve, something like this, very, very mild slope, and you have a car that was like 120 miles per hour, it might get out of the curve, like he cannot control himself. He needs much bigger slope to balance the centrifugal force, which coming from the normal acceleration, okay? So let's put an example and see how this works. Like let's say I'm gonna take a cross section here, okay, and I'm gonna look like this. You guys, the cross sections and profiles, is that okay? So we can imagine that. So if I take a cross section, it's gonna be, for example, something like this. And let's assume that there's a car here. So let's, like, for example, I'm gonna see, like this is the tires, and actually this is the windshield, and somebody is driving at the wheel over there, okay, and this is the tires. Alright? Okay, let's do analysis for the forces on this car. But before I do analysis, let's put, as I said first, we need to understand the problem and then bake the coordinate system. Let's say that I'm gonna use tangent normal coordinate system. Do you guys tell me if this is the curve, where is the tangent and where is the normal?
The normal.
And the car is moving this way, like my car is this way and coming this way. So definitely the tangent is with the velocity, right? And tangent to the curve, like this is the center line of the curve, and it's tangent to the curve. If it's here, it's gonna be something like this. All right, if I wanna project this tangent direction on this cross section, how it's gonna be?
It's very cool.
It's like a point out of the plane, because I'm here, and this is coming out of the plane, like I can see there's a curve. It's gonna show as a point, because if you have a line like this, but if I look like this, it's gonna show as a point. Okay, so this is the tangent coordinate system. How about the normal? It's gonna be towards to the center of the curve, something like this. So this is the normal. So if I wanna draw the normal, and actually this is how the curve looks like. So the normal, is it gonna be inclined or is it gonna be something like this? It's not gonna be inclined, okay? It's because I don't care about how the slope is, it's just like the circle, and this is the center of the circle. So this is the normal direction, let's say, and vector. And the tangent is out of the plane. And actually, let's write the tangent so you guys can see it. But this is not in the plane. This is something, let me write it 3D. Let's make it something like this. And this is out of the plane. This is the tangent direction. And if you want to write the z direction, which is the vertical, it's gonna be something like this. All right. I put all the coordinate system. I have the n hat, the z hat are in this plane, and the t hat is out of the board. Okay? So I put the coordinate system. Let's put all the forces on this car. What kind of forces acting on this car? Definitely the motor of the car, because the motor is keep the car moving. And what is the direction of the motor? It's in the tangent, right? Because this is how the car is moving. So the motor is pushing the car this way, which is the same direction of the tangent, the same direction of the motion. Okay? So the motor of the car, like I want to put it, let's make something like this, and let's say F motor, and this is the direction of the force. What other force is acting on this car?
Weight.
The weight, right? How does the weight look like? Where does it come from?
Down.
Down. It's always in the gravity. It's in the negative z direction. Whatever the motion looks like, it always goes down something like this. The weight of the car, which is mg. What else?
Normal force.
The normal force. How can I put the normal force? It's always perpendicular to the surface. If the surface like this, it's like this. If the surface like this, it's always perpendicular to the surface, whatever the surface shape looks like. So, if this is something like this, so definitely the normal is something like this. Okay, what else?
Friction.
The friction. How is the direction of the friction?
Against the velocity.
There's one against the velocity, but I don't care about it because I can't put it, but it's gonna act on this one. What else? There's two frictions. One when the car is moving, so when the wheel of the car is moving, she needs to overcome the friction from the ground, right? So there's one in the direction of the car. And there's one that makes the car don't slide on this curve, okay? So if the slope, if the weight wanna go this way, so the friction definitely is gonna be this way. So this is F friction. So that's what I need you to do whenever I give you any problem. You understand the problem, pick the coordinate system, put all the forces here. Yeah.
Can you repeat what force M is?
Fm is the motor of the car, like the F motor. Like the car is moving, it needs power. The power is coming from the motor of the car and keep the car moving. If I told you that this car has a motor that gives it a force of equal to 1,000 newtons, so I'm gonna put the 1,000 newtons.
The tangent, is it parallel with the ground or it's?
No, the tangent is out of the plane. It's like this. Like this. I cut the section here. That's why I didn't want to put the tangent to confuse you. Like the tangent is not in this surface. It's coming out of the plane. If it does, if this confuse you, so we can remove this. Because I can't draw in 3D, so I only have 2D board. And the tangent is coming out of the plane.
Okay.
Something like this. And the motor is also in this direction. Right? Okay, so right now we understand. So you guys tell me the steps of solving problems. What is number one? Like if I want to solve number one,
The forces.
Before the forces, what did I do? Draw the coordinate system. Which is tangent, normal, and if you have z, so you put z. And always keep attention to if I'm saying the body is moving on a horizontal curve or on a vertical curve. Because this is very, very important. This car is moving on a horizontal curve. Like this curve is in the plane. But sometimes I give you like a bar in the vertical direction and there's something is moving on this bar. So the curve is in the vertical direction, but this one is a horizontal. Okay, number 2, you need to draw the A tangent draw A tangent and A normal. So if I want to know where's the A tangent and A normal, that's very easy. Once you decided where the tangent and normal direction, so definitely here is the A normal direction, and the tangent is coming out of the plane. Number 3, add the forces. And that's what we did here. We draw the coordinate system. Number 2, we can put, once we have the coordinate system, we can put the acceleration direction, and then we decided where are the forces. Okay, so let's solve an example. The best example for curvilinear Newtonian motion. Example. I forgot to print the text of the problems, but I'm gonna tell you how this problem looked like. Let me see. Okay. So it's a swing problem, like you have somebody is sitting on a swing, like let's say this is the fixation up there, and the swing has 2 chords, and there's a chair here, and somebody can sit here on this swing, okay? And if I look on this, is how this swing moves, it moves like this. So if I want to capture the curve that this swing is moving on, this one is not going to tell me, because every time if I'm looking at this swing this way and it's moving this way, I will not be able to see the curve. So I need to look this way so I can see how this swing is moving. So when I see the other way, these 2 lines or these 2 curves are going to show as a one line, something like this. And the swing is going to be swinging this way, and here you are going to have the mass of the chair and the mass of the body. We can represent it by something like this. So I'm telling you in this problem, a 60 pound person. So the weight of the person is 60 pounds. Swing from 60 degrees below the horizontal to the vertical. So this is 60 degrees, started at 60 degrees. If the swing started at rest, so I'm telling you that somebody stopped here and started at rest with 60-degree angle and let himself to swing, I'm asking you to determine, number 1, the final speed, and number 2, the tension in each route. Tension when at this moment. Okay, so let's understand the motion here. I'm gonna write it here. Okay, so number 1, I need to draw 2 things. Do you guys remember? the kinetic diagram and the free body diagram. What is the free body diagram and what is the kinetic diagram? So I'm gonna draw the free body diagram here. I'm gonna draw the kinetic diagram here. Let's understand the motion. So this moves on a curve, and I told you at the verse that the radius or the bar is 10 feet. So I have this 10 feet, and this is 10 feet. What coordinate system that I'm gonna use for this problem, which is very simple? It's radius, so it's gonna be tangent normal. Let's first put the coordinate system. All right, so I'm gonna put the tangent in this direction. This is the tangent, and this is the normal direction. Okay? So I'm gonna have the acceleration tangent this way and the acceleration normal this way. Right? So I put the accelerations on the kinetic diagram. Let's put, what is the forces acting on this body? As there is a friction, there's no friction. We are gonna neglect the air friction. Is there any tension, right? So what is the value of the tension here? This angle is 60 degrees, don't forget that. So I'm asking the tension in each rod, okay? And I have two, so keep attention to this. So I have tension here and tension here. If you put only one T here, so that means that you get two tension in one. And I'm only asking for one. You need to divide it by two when you get it. So to be cautious, I'm gonna call it 2T. Okay, what is else? What else? The weight, right? The weight is going down this way. And it's equal mg, and I'm giving you in bounds, so that's directly is the weight. What is the next step? The next step is to do the Newtonian rule, which is the sum of the forces equal the mass multiplied by the acceleration. And since I have two, so I have one in the tangent, one in the normal direction. But before I do this, let's do some geometry and identify some angles. I'm gonna draw a tangent here. Okay? I'm gonna draw, this is the tangent direction and this is the normal direction. Let's get some angles here. This angle is 60 degrees. So what is the value of this angle?
60.
What is this?
30.
30, right? How about this? If this is 30, what about this one? 60 degrees. Right? So I know that this angle is 60 degrees. So let's start seeing what components are in the tangent direction and what components are in the normal direction. I'm gonna start with, let's put here, I'm gonna say here, 4 tangent direction. The sum of the forces in the tangent direction equal MA tangent. What is the forces in the tangent direction? Does the tension in the cord has any component in the tangent?
The tension, no.
The tension, no, right? Because it's all going in the normal direction. The only thing that has a component, not the all force, in the tangent is the weight. And this component is cosine or sine? This is the 60 degree.
Cosine.
The cosine component. Is it positive or negative? What? Positive, right? Because this one was gonna have a component this way and component this way. So I have W cosine theta is equal to the mass multiplied by the A tangent. Let's get to the other direction. For n hat direction. Sum of the forces in the n hat equal ma n hat, an. So what is the components in the normal direction? I have directly 2t, it's positive. What else? How about w? Does it have any component in the normal direction? The sine component, is it positive or negative?
Negative.
So negative w sine theta equal man. Let's put numbers. I have w equals 60 pounds, so that's w cosine theta. I'm gonna leave theta right now and I'm gonna tell you why. How about the mass? How can I get the mass? I have the weight, so I'm gonna divide the weight by 32.2 multiplied by a tangent. So I can cross the 60 with 60, so a tangent is equal to 32.2 cosine theta. Is this a constant acceleration or not? Why? Because there's theta. So if the theta is 0, it's gonna have different acceleration. If it's 30, so I'm gonna leave it like this. Let's get here.
Why isn't the tension at an angle to it's just straight up? Or-
Yeah, the tension is in the chord direction, and this is the same.
That's a coordinate. Okay.
Like the road, like if you have
Yeah.
like a rod or something, so it's in the same
Okay, perfect.
direction. That's why we use tangent normal, because that makes the motion easy.
Why are you dividing the 60 by 32.2 and not 9.8?
Because it's given in pounds. So if you have the units in pounds, you need to divide by g, which is in feet square per second, or feet per second square.
Oh, okay.
And this is equal to 32.2.
What units does it give it to you in?
Hmm?
So 60 divided by 32.2, what unit is that?
This is gonna be
Slug,
slug.
right?
Yeah. Alright, so I have a tangent. Let's get here. So here I'm gonna have 2t minus w, which is 60 sine sine 60 equal to the mass 60 over 32.2 multiplied by, what is the A normal? We always know that the A normal is v squared over rho, and I know rho is equal to 10. So right now I have the tension as a function in velocity. So let's put everything together. So I'm gonna have tension is equal to 1 over 2, because here I have 2, so I need to multiply by half. And then I'm gonna send this to the other side. It's gonna be 60 sine 60 plus 60 over 32.2 multiplied by v squared over 10. Does anybody have any problem with what I did here?
No.
I send this to the right hand side and I divide it by 2 to keep the tension alone, okay? And that's what I was asking here, the tension in the row, okay? I have this equation in the velocity. I want to get the velocity, which is the requirement number 1, so that I can get this, the second one.
The velocity squared over 10, that's solving for an, right? Or
And yeah,
over-
that's the equation. The normal acceleration is equal to the v squared over rho. That's what we wrote here. And that's from the last chapter.
Oh, because it's 10 feet long. Okay.
Yeah. Alright, so I need to find the velocity. What I'm gonna do? So this equation actually solved everything. If you know the velocity, you are gonna substitute here and get the tension. But what I'm gonna do, I'm gonna use this to get the velocity. And this is not constant acceleration, so we need to remember the rules to calculate velocity. Do you guys remember? The velocity is dv dt, right? And we said that we can make this dv ds multiplied by ds dt, right? So that we can cross the ds with ds and it always end up with dv dt. But this one, ds dt is v, is the velocity, right? The time rate of change of the position. So this is equal v dv ds, and this is the rule that you have. ADS is equal to v dv. Do you guys remember this rule? All right, so the thing is, I have a with the derivative of ds, but right now I have a is changing with theta, so I need to find the relationship between theta and ds. So let's find out what is this relationship. Okay, if somebody's moving on a curve, and it's here, like it's the position.
Oh, no.
And I'm gonna take an infinitesimal distance, something like this. This is the center. And the body moved from this point to this point. We are gonna call this ds. And the angle here is d theta, you guys remember? And this is the radius. Let's make it grow. What is the relationship between ds and d theta? ds is equal to, you guys remember? If I wanna find a piece of the curve, like if we want to find the perimeter of the circle, it is 2 pi multiplied by r. This angle from here to here is 2 pi multiplied by the radius r. What if I want to find just 1/4? So it's gonna be pi over 2 multiplied by r. If you want to find a small piece, so it's gonna be d theta multiplied by rho. Rho d theta, and I explained this very detailed in the second or the third lecture, that the curve length is equal to the angle in radian, not in degrees, multiplied by the radius. Okay, so I can say here that the acceleration multiplied by ds, I can remove ds and put rho d theta is equal to v dv. So I can put the acceleration as a function of cosine theta right now, so I can say that 32.2 cosine theta multiplied by rho, which is 10, and I have here d theta equal to v dv. So right now I have a differential equation. If I want to solve it, I need to integrate this equation.
Is that 32.2?
Yeah, 32.2, which is the acceleration here. So if I integrate from here, what is the boundary of the integration? It is the angle theta. Where did it start from? It start at 60 degrees. And he wants us to calculate when the body gets here. So when it gets to 90. So here from 60 degrees to 90 degrees. And I made it clear in the statement of the problem. When the body started at 60 and stopped at 90. How about the velocity? In the problem I said the body started from rest. So the velocity was 0. And it ended up here, which the velocity I don't know. That's what we are looking for. Find the final speed. So from v equal to 0, v node equal to 0, up to v. Once you do this part is going to be the integration of v dv. How's it going to be? V squared over 2. And when you substitute with the boundary of the integration, so it's going to be v squared over 2. And when you substitute, it's going to be v squared over 2 minus 0. So it's going to be still v squared over 2. How about the integration of this part? So when you multiply 10 by 32.2, it's going to be 322. The integration of cosine theta. Sine theta. And you put the boundary of the integration 60 degree to 90 degrees. So right now we need to find what is the value of this. Then you can find the velocity. Once you do this, you all know. So what you are going to do, you are going to make 322 multiplied by sine 90 minus 322 multiplied by sine 60. Yeah.
In this case, you're using degrees as a degree, but earlier you said you have to do the degree in radians.
Yeah, it depends where are you going to use it. Like if you are going to calculate a curve length, it's going to be radian. You can actually calculate the sines with radian, but you need to change the calculator setting to put the angles to make it in a radial mode. If you put it in a radian mode, so you can get sine theta, it's going to be accurate. But if you make it as a degree and put theta as radian, it's going to give you wrong numbers.
So just keep it consistent.
Keep it consistent. But definitely, if you are calculating curved lenses, so it's definitely radial.
How did you get the bounds 60 degrees and 90?
It's given in the problem that the body started at angle 60 degrees, so I know the initial boundary, and it asks for the velocity here when it's 90. Okay? So if I ask you the velocity when it gets here or gets anywhere, so you put the new boundary condition.
Can they specifically say like from 60 to 90 or?
Yeah. Okay, so the velocity is gonna be, once you do the calculation, (9.29 per second). And once you calculate the velocity, you can substitute here and get the tension. So it's gonna be 38.01 pound. By the way, this is only one tension. If the two tension, if you put 2T, it's gonna be 76.18 pound.
But you have to do
So I need you to like 2T is equal to, if you multiply this by 2, it's gonna be 76.18 pound. This is 2T. Can you guys notice something? The tension in the swing rod is 76 pound and the weight of the guy is 60 pound. So this is more than the weight of the guy who's sitting on the swing. Why? Because of what?
Acceleration?
What kind of acceleration?
Centrifugal.
Because the normal acceleration. Why? Because you need extra force coming from the rod to keep this guy on the curve. Doesn't go away. So it needs to resist two things: the weight of this guy and also the normal acceleration, so that you can keep him on the curve. All right, you need to understand this stuff. Because sometimes I'll ask you to explain things. Why this is bigger than this? Like when you get T, I'll ask you, is it bigger than the weight or more? And explain. Okay? Because anybody on a curve, the body needs to exert more force to stay on the curve, to overcome the normal acceleration. Okay, does anybody have any question?
Yeah. I want to know how you went from ADS to AD data again.
Okay, 1 second. So what we have here, we got the A tangent is equal to 32.2 cosine theta, right? That's function in theta. But the equation that we have for the acceleration is ADS is equal to VdV. That's the equation that we have from previous. So what we want to do, we either convert the cosine theta to be function in ds, or convert ds to be function in theta. Because if I have this, if I substitute here 32.2 cosine theta ds, I can't integrate this. I need this to be d theta. So I need to find the relationship between the length on the curve and the angle theta. And how we can do it, if you guys, this is from math. I have a circle, and you need to find what is the perimeter of this circle. You multiply, what is the name of this angle? It has a name, right? I know it in Arabic, but I don't know it in English. So, yeah, so there's this angle has a name. I'm not sure, like surrounding angle or something. And this is a curve. Okay, so this is the curve opposite to the angle. Okay, so if you want to find the length of this curve, it's always like, let's say it's S. So S is equal to the radius multiplied by the theta. Let's say this is theta, R theta. And this actually proves the equation of the perimeter of the circle. Like if you want to find all this length, so the theta is equal to 2 pi R, and you put 2 pi, and this gives you 2 pi R. If you want to find just 1/4 of the circle, so this is going to be divided by 4. 2 pi over 4, which is the 90 degree, multiplied by R. If you want to find a small peak, so it's any angle theta in radian multiplied by R, it's going to give you
In radian.
yeah, in radian. Because when you multiply, when you get 2 pi by r, 2 pi is 360 degree, but we put in ingredient, it's 3.14 multiplied by 2. That's what we did here. That's why we removed this, and we put r d theta, and that's why we make this equation consistent function in theta. Okay? I don't want you to forget that we sometimes the body's not gonna move on a circle. So if it's moving on a general curve, you guys remember how we can get rho if I give you the body's moving on a curve fy is equal to 3x squared plus 2x. So there's an equation for that. It's 1 plus dy dx all the square, and all this is to the power 3 over 2. And here is d squared y dx squared. That's how you get the rho. Sometimes the motion is not on a circle, so you will have to find the rho by this rule, which is in the equation sheet.
So going back to the example, the final answer for this problem will be 2t equals 76.18 pounds.
This one?
Yep.
The 1t is 38.01. 2t is gonna be 76.18. Oh, you solved it? That gives you a different number?
No, I was asking if that was the final answer.
Yeah, this is the final answer. Right, we are gonna solve another problem to make sure that we have everything good. So we have like a skater, and this is skater is skating on a half circle. Like there's a half circle like this, and let's say there's a cross system holding this part. Okay, and this is like a field that somebody is skating on it. It's almost the same problem actually. I'm going to tell you just the idea. So the radius of this circle is 4 meters, and this skater started at angle theta, and it has a mass, let's say example 13.9. The mass is equal of this body is 16 kilogram. The radius is 4 meters. That's all. And you have somebody is skating here, and it started at angle theta, which also is, it says that theta is equal to, theta node is equal to 0. We start from 0. This is theta node, and the theta final is 60 degrees. Start from here and end up here. Okay. So what I'm gonna do, I'm gonna take the same body, put it here. I'm gonna draw a free body diagram. Let me do it up there. So I'm gonna do a free body diagram. This guy is make a free body diagram, and kinetic diagram. I'm just gonna give you the idea. I'm not gonna solve it to the end because it's the same problem. So this body's moving this way. Where's the tangent direction? Start from here and going this way. It's definitely tangent to the surface. Up or down? Down. It's going this way. So this is the tangent. And the normal? And that's the very thing that you should do. Don't mess it up, because if you mess it up, it's gonna mess your whole problem. If you choose the XY coordinate system, you will end up nowhere. Okay, so tangent and normal. And then let's put the forces. The difference between this one and this one is what? There is no tension, but there's other things here. That's right. So we don't have any tension here because this is a free skater. So let's put the first force, the most easiest one is what? It's the weight, right? It always goes down. And what forces that I have here? I have normal and friction, so the normal is always perpendicular to the surface. So if this is the surface, so it's perpendicular. Okay? It's going this way, so you have normal. And actually, I believe I given this problem to neglect the friction. Okay? So I said that it's a smooth surface. So once you hear it's smooth, so that means that you need to neglect the friction. But if I didn't say that, and this body's moving this way, the friction is gonna be this way. But in my problem, F of friction is equal to 0. Okay, so let's talk angles. Use different colors here. This angle, start from 0, and I want you to calculate the velocity at 60 degrees. So I have this angle is 60 degrees. So if I put this like this, so this angle is equal to this angle, right? Equal to this angle, equal to this angle. So this angle is 60, and this angle is 60, and this angle is 60, because this one and this one is 90, and this one is 90. So I know what are my angles is. So the second thing that I want to do is, I want to do in the tangent direction and in normal direction. Sum of the forces in the tangent equal MA tangent, and sum of the forces in the n direction sum is equal MA tangent. So let's find out what is the components in the tangent direction. Does the normal has a component in the tangent direction? It's perpendicular to the surface. It's all in the n hat direction, and it's positive, so I can put it here right now. Right? So n doesn't have any components. Let's see the weights. Does it have any components? Yes, it has. And it has in both directions, tangent and normal. So what is in the tangent direction, the cosine component or the sine component? Is it negative or positive? I need you to think. Well, W is going this way, so it's in the positive direction. So W cosine theta equal to M A tangent. Let's get here. I have all the normal is in the positive direction. How about the component of the weight? Positive or negative?
Negative.
Negative. It's going the other way. So minus W sine theta is equal to the mass multiplied by V squared over rho. We're gonna do the same thing. I have the weight, I have the mass is given 60 kilograms. Right now, because of the units, I have 60 kilograms and I'm gonna multiply by 9.81. Then you find out what is this value is. So 60 multiplied by 9.81, I'm gonna keep it cosine theta equal to the mass, which is 60 multiplied by A tangent. I can cross the 60 with the 60. So I'm gonna have A tangent is equal to 9.81 cosine theta. I'm gonna do the same thing here. I don't know what his n is. So I'm gonna put it, n is equal to And actually I'm asking about the value of the n at the end. It's gonna be 60 multiplied by 981 sine theta, which is gonna be 60 degrees, plus the mass, which is 60 multiplied by v squared over rho, and the radius is 4. So this is the equation of the normal force. So what I'm gonna do here, I'm not gonna continue, because it's the same steps. I have A tangent as a function in theta. So what I'm gonna do is, to get the velocity, v dv, I need to convert ds, so it's gonna be A tangent multiplied by r rho v theta, v dv, and then I integrate, and then I get the v. Once I get the v, I substitute here with the v here to get the normal force. You guys got that? It is the same sequence. I get the A tangent as a function of theta, and then I substitute with ds by rho d theta, and I get v. Once I get v, I substitute in. That's what the same thing that I did here. I have A tangent as a function in theta, and once I get it, and I integrate and get the velocity, I substitute to get the tension in the rod. Same thing. I think I have a extra problem, but I'm gonna leave it for you. It's example 13.6. It's a car moving on a track, like a Formula 1 or something. And you are gonna put the forces, the friction, everything. It's like the car example that I have from first example. But it has an interesting thing. Maybe I'm gonna print it and give you a look at it. So what I did to you, I asked you about the slope of the curve that makes this car doesn't slide. Like if you have a car is moving on a race, something like this. And I ask you about what is the angle theta that can keep this car not sliding. So I did the z direction, I did, okay, it has z direction and tangent. Okay, let me solve it. You guys,
okay, so he substituted here, he substituted this, he substituted this.
so the same car example that we had from before, I told you that like it was something like this. And you have, for example, like this is the tires of the car.
Okay, so 80 doesn't. Oh, okay.
Okay, and it's moving this way. And I give you, and all the problem, like this is example 13.6. I didn't give you numbers. I told you that the mass of the car is m. And I want you to give me the final slope angle, like the theta of this. Find theta that can keep this car not sliding, okay? And neglect the friction. Like without the friction force, like, and this is actually extra safety. Like, okay, the friction is gonna, like this car, if it wanna slide this way, okay, the friction is gonna resist, right? But I want you to keep this car not sliding, assuming there is no friction. Like this car, when she's taking this curve, it loses friction with the surface. How can we keep it on the curve? All right, so that's actually given. So since I give you the mass, if you want to get the weight of the car is equal to mg, and we said that F of friction, which is equal to mu multiplied by the normal force, we are gonna assume that this is 0. All right, so let's put the forces on this car. And we discussed this. The first thing that we have, let's make it easier. I'm gonna put it as a mass here. Like this is our car. The first force that I have is the weight. I have the normal force this way, and if this car is gonna slide this way, I have friction this way. So if I ask you not to neglect the friction, so you are gonna put it this way. Do I have any other forces? No, I don't. And I want to make another one for this is the free body diagram, and this is the kinetic diagram. This is the body. You guys tell me where are the direction of the tangent normal? The normal is like this.
Yeah.
The tangent is out of the plane, and z is going up. This is z. In this problem, I have z. Why? Because the weight is going down, so the weight is in the z direction, so I need to make a component for z. So let's just start. I'm gonna talk about the tangent right now because the tangent is out of the plane and we don't need it in this problem, but we are gonna see if we need it or not. So let's solve this problem. Number 1, z direction. I will tell you now why did I do z direction first. The only component that I have in the z direction, let's see. Let's put the angles. If this is angle theta, theta, and if I made a horizontal like this and vertical like this, I have W is in the negative z, and normal is going this way, then this is the normal. Let's see, this angle is theta, and this one is 90, so this angle is theta. And it's going up. So is the normal, what is the component of the normal in the direction of z? This is the z direction, and this is the z direction, and this is the normal force. If you want to get the two components, can have component this way and component this way. So what is the component in the z direction?
Cosine.
The cosine component. So you have n cosine theta. How about the weight? Does it have components?
It's only in the z.
It's all in the z, so it's in the negative z. So minus w equal to the mass multiplied by the acceleration az. Sum of fz is equal maz. Is there any acceleration in the z direction that this car moves vertically? No, so this is equal to 0. So right now, if you want to find the normal force is going to be equal to n is going to be equal to w, which is the mass multiplied by the acceleration over cosine theta. Right now, I got the normal force, right? Let's get the normal direction. In the n direction is the same thing, sum of the forces, MAN. What is the forces in the n direction?
Just normal sine theta.
By the way, F of friction is equal to 0, so don't get confused. But sometimes I can give you friction, so you have to include it in the problem. So I have component from n in the direction of the n hat, because n is going this way, so we have the sine component is in the positive direction of n hat. So you have n sine theta is equal to the mass multiplied by an. What is the value of an? V squared over rho. Okay, I have n is equal to mg cosine over cosine theta. I can substitute here. So let's put this this equation number 1, this equation number 2, substitute 1 and 2, so replace n with the value of mg cosine theta, sorry, mg over cosine theta, and I have sine theta here is equal to the mass multiplied by v squared over rho. I can cross the mass with this mass here. And what is sine theta over cosine theta equal to?
Tangent.
Tan theta, right? So you have tan theta multiplied by g, but I'm gonna divide by g here, equal to v squared over rho g. So if you wanna get theta, so it's tan inverse v squared over rho g. And actually this is very, very important equation in designing the geometric design of curves in transportation networks. This equation. And it's independent of the mass of the car. Whatever the mass of the car, if you have small cars, big cars, moving on this curve doesn't matter. What matters is the velocity, the radius of the curve, and actually the gravitational acceleration, which is constant. That's what I told you at first. Whatever the curve is, the theta of the super elevation, like if you have a super elevation like this theta depends on the maximum speed limit that you put on the front of the road. So when you tell a car don't move 45 miles per hour, it has a meaning because I designed the super elevation with, definitely there's a factor of safety, but this is how I design it, like with this speed. And actually the radius is constant. So what is the only variable on the road? Is the velocity of the car, because I already have the bridge is designed. I can't, like if a car is moving in the bridge, I can't change the radius. The radius is constant. All what you can change is decreasing the speed of your car so that you can maintain normal acceleration or centrifugal force on your car that doesn't exceed the limit so that your car doesn't thrown out of the bridge. Okay, so this is very important equation. Yeah.
Okay, for the z direction, it was cosine on which angle?
Okay. This normal force is this way.
Okay.
Okay? And actually, this is the theta of the super elevation. This theta is equal to this angle.
Okay.
Okay? And this is 90 degrees.
Yes.
And this is 90 degrees. So this angle is equal to this angle is equal to theta. And normal force is this way, so the cosine component is in the z direction. And the sine component is in the normal direction. Because theta is here. If theta is here, so this is gonna be the cosine and this is the sine, but theta is here.
And then for the n?
Like here is the normal, and this is theta, so the cosine component here and here. But if this is theta, so the cosine is here and the sine is here. Unless if I give you information that I need something about the tangent. In this problem, I don't need anything else. You can put the tangent, but I have to give you, for example, the motor force and everything, so you do analysis to get the velocity of the car and stuff like this. But I didn't ask about the velocity of the car. All I'm asking about is the theta. Okay. Any more questions? All right, let me use this 10 minutes to introduce chapter 13.6. We are going to deal with polar coordinate systems. And this is R and theta. By the way, R and theta, same thing. The forces are going to be, we're going to use the same Newton's second law. Sum of the forces equal to the mass multiplied by the acceleration. And that means that sum of of the forces in the R direction equal MAR, and you guys need to find out what is the value of AR is from the last chapter. Sum of the forces F theta is equal to MA theta, and if Z, sum of the forces in the Z direction is equal to MA Z. And if you want a refreshment of the value of AR, R double dot minus R theta dot square, A theta is R theta dot plus 2 R dot theta dot. It's in the equation sheet. All right, let's figure out how this coordinate system is gonna work in the Newtonian kinetics. So let's assume that we have our bodies moving on this curve, and this curve position R is described this way. Do you guys remember how can we draw the R theta directions? R is in the direction of this R, right? It's gonna be something this way. If it's a circle, something like this, it's the same way. Something like this, R direction. How about theta? I told you that this is the direction of increasing theta. So theta hat, what is the direction of theta hat? It's perpendicular to R in the direction of increasing theta. So it's something like this. This is theta direction. If I want to plot the tangent normal on these curves, how can I plot them?
Normal would be this way.
The tangent, let's start with the tangent. The tangent is always tangent to the curve, right? And this body's moving this way, so I have the tangent something like this, right? How about the normal? Towards the radius, and it's always perpendicular to the tangent. It's going to be something like this. So this is the n direction. I want to introduce you to a new angle that we are going to use in this application. The first angle that we already know is this angle. What is the value of this angle?
Theta.
Theta, right? Because this angle is theta, so this angle is going to be theta. So if you take any horizontal line parallel to this is going to be theta. I'm going to introduce you to a new angle which is between R vector and T vector, R hat and T hat. This angle is called XC, and the value of this angle is proven to be, and I believe it's in the equation sheet, is equal to tan inverse R over dr d theta. So you will be given R as a function of theta. You get the derivative of dr d theta, and then you are going to have an equation, and then you substitute with xc at any value of theta, so that you can get the value of R and value of dr d theta. So this is a very, very important rule. Sometimes we will need this. Okay, so let's find out what type of forces that we can have on a body. Types of forces. Types of forces. Number one, we can have a normal force, normal to a pushing R. I'm gonna give you some ideas in this problem how the forces can be look like. So normal to a pushing R. Usually this problem is something like this, like for this application. Like you have a circular, or not a circular, like a curved path, something like this. And I give you R as a function of theta for this curve, and this is the sum. Okay? So you can find actually the radius R at any point, like the radius R here. It can be an ellipse, it can be a circle, it can be any general curve. And I give you an R and and this arm has something like this that allows this arm to move on this curve. So if I'm saying that this arm is moving with a pushing force, like this arm is moving this way, so there's a force that pushes this arm, so this force is always perpendicular to the arm. Like if this is the arm and this arm is pushing this way, so there's a perpendicular force this way. And sometimes I ask you, what is the pushing force that this arm is exerting on this back? Okay, so the pushing force is always perpendicular. Like if this is the center and this is the R direction, so always the force, and this is moving this way, the force is always perpendicular to the R. So this is B. Okay, so what is the direction of the force? If I'm telling you this is R, the arm is this way and the pushing force is this way. So it's in the theta direction, right? Because it's perpendicular to the arm. And if this is R, this is going to be theta, because this is the direction of increasing theta. So it's always in the theta direction. So if I want to map this force over there, so it's going to be this way. B. Assuming that this is my arm and this arm is moving this way to keep this point on this path, so there's a pushing force that this arm is exerting perpendicular to the path. And that's what I'm talking about here. So R, the B, the pushing force, is perpendicular to R direction. It can be along the positive or the negative theta. Okay? You'll tell me, okay, I'm pushing this arm this way, and this arm is moving down. But this pushing force should be in the positive direction of theta. No, it doesn't. Maybe there's other forces that can make the arm moving to the other way. Okay? So number 2, the friction force. Okay, the friction force is always along the path. Okay? And it's in the negative tangential. Okay, so let's assume that you have your body here, and the friction force that this body is moving, it's always tangential to the path. Like, it is something like this. Like this body is moving here, so it's always tangent. And if this one is moving in the tangent direction, like let's assume that this point is moving this way, so the tangent, the friction is going to the other direction, F friction. It's always in the negative tangential direction. Okay? How about the normal force? The normal force is the force that, like if like a body is like here having a weight, so the normal is in the positive or the negative n-hat direction. Okay? So this is the surface, so the normal is always normal to the surface, something like this. This is n. And that's actually what we did in many applications. Like if you have a body is moving here, so that's what we did, it's perpendicular to the surface. Something, this is n. And if the body is something like this, it's perpendicular to the surface. If it's curved, it's perpendicular to the surface. Always going in the positive n-hat direction. So this is the surface, so this is the n-hat direction. Number 4 is the weight. The weight is always going down. Like if this body, if this is the z direction, like if this is xy plane, so this point is moving down. So the weight is always in the negative z direction. That's the end of the lecture, but I wanted you to keep attention to these forces because many of you may mess up problems because they cannot map the forces. Like if you put a friction, make sure that the friction is tangent to the surface. You put a normal force, it's perpendicular to the surface. See you guys next time. Next time there will be a quiz on Thursday. No, just review the notes. And I hope it was done.
I cut it out and I'll put it in.
That's just definitely will be new.